Okay, let's go on. Stats 101A, and we're going to go on more inference on simple linear regression here. Okay. So Monday's lecture focused on two main objectives, which was estimating the parameters of the linear regression model. Okay, so getting that slope and intercept, and also estimating the variance in the population. And then we also performed inference on those parameters that we created estimates for. Okay, so that's not much. It's not unlike in intro stats. You find the mean of a sample and then you perform inference on that sample statistic, right? Except finding the mean is so easy that you don't realize that you're actually estimating a population parameter, okay? Or maybe you recognize that. So, but here it's a little bit more involved estimating the parameters, but it's not that big of a deal once you get the parameter estimates. But then, of course, you always want to do inference and just say, what does this then mean about the population? So we created confidence intervals and we performed hypothesis tests on those things. Oh, look at that. This is what I was saying. So specifically, we learned to estimate the slope, intercept, and variance. And then we performed hypothesis tests for slope and intercept and confidence intervals for the slope and intercept. And then I briefly showed how to do these things with R. Okay, so today we're going to perform more inference, and we're going to create confidence and prediction intervals for the regression line. So that's really exciting. And we're going to perform ANOVA, analysis of variance of the regression model. Have you guys had ANOVA before, exposure to ANOVA? Just a tiny bit. Okay, all right, so I was wondering, like, am I going too basic in the description of ANOVA here? But I feel like if you guys are shaking your head, then I'm describing ANOVA to the appropriate amount here. Okay, so this is the data. We're going to still use the same production data. We're calculating the run time, or we're creating estimate for run time based on the run size. Okay, so we're relating y to x, and these are the commands. We just do this in R. Linear model of runtime based on run size, where your data is the production data. And we're going to store this into the object model. Okay, so now, so on Monday we covered inference for the slope and inference for the intercept. And now we're going to perform inference for the regression value y itself at x equal to x star, okay? So we're basically combining those inference results, and what we want to know is what can we say about y when x equals to x star. So this is what we're going for here, okay? So this is a parameter, right? This is some value in the population that is unknown to us. This is the expected value of y kind of in the long run when x takes on this particular value x star. So this is a population parameter. Okay, it's just that there's lots of x stars, so it's a line. Okay, so pretty much just like everything else, when we create a confidence interval, we've got the estimated value plus or minus the t star times the standard error. Okay, and so I've skipped the math here, if you'll forgive me. For the standard error of this thing, and this again is the derivation of this result is shown in the book, okay, in section 2.7. So you can find this, but pretty much our estimate of y at x equal to x star is this quantity. Okay, so this is the value of the fitted line at x star, beta 0 hat plus beta 1 hat times x star. So if I just said, give me your point estimate at x equal to x star, you would say this is our estimate right here, okay? Plus or minus t star times, and then this is the standard error of this estimate, okay? So just, again, I've kind of skipped the math showing how we got here, but this is what we have. Good? Okay, so if we want to create a confidence interval, we can pull all of these things from our model, right? So we need each of these things, right? Beta 0 hat, beta 1 hat. We need the t, we need the s, we need the n, and the sxx, and all of these things, okay? And we can get that, okay? So each of these things, you know, the sigma in our model is s. Sum of squares x is our variance times n minus 1, all of these things. And then so our estimate of what y star is b0 plus b1 times x star. And then our lower bound will be our estimate minus t star times the standard error. And our upper bound will be our estimate plus t star times the standard error. Okay, and we get that. And when we punch this out, so here's our estimate, go down, go up, this is our lower bound and our upper bound. Okay, again, so I've shown like a lot of this stuff because I think exercise 3 in your homework forces you to kind of use the results and figure these things out rather than using the built-in functions. And some of the things where you're doing hypothesis tests require you to do these things by hand. Okay, so anyway, but if you're not trying to do all of this by hand, R does it very nicely for us. We just use the command predict. And the arguments that predict takes is the model that we have created. And then you have to supply it a value that you want it to make a prediction for. So in this, and it has to be a data frame. So you say data frame, and we want run size equal to 150. And then we're going to say create a confidence interval for this. And ta-da, it does that, which is exactly what we got when we did it by hand. So R does it. So that's nice, right? Graphically, this is also implemented for us. So this is just ggplot. You say take your production data where x is run size, y is run time, graph the points, and then add a smoothing line, okay? Now if you just want the smooth line, you say SE equals false. But if you want, if you take off the SE equal false and you just say stat smooth method equal to LM, it puts in the 95% confidence interval for you, okay? So this gray area is the 95% confidence interval. So we have our estimated line, but the, so remember, with a regression model, we're saying in the population there is some line that relates x to y in a linear fashion. We don't know that exact line. This blue line is our best estimate. This gray zone is our 95% confidence region for the true line, okay? And this is what it looks like, okay? And we notice, did I talk about this? Okay, yeah. And so this is just to show that indeed, if I were to graph the points 179.997 and 197.271 at the point 150, we see that that is exactly the width of our confidence interval in ggplot2. I'm not just saying that this is the 95% confidence interval. It really is, okay? So, yeah, this is what I want to say. So keep in mind that this is a confidence interval for the regression line. So our model assumes that there is a linear relationship between x and y in the population, and this line is unknown to us, okay? And so for a certain value of x, we can create an interval that will capture the mean regression value of y with 95% confidence. And when we created the graph, we noticed that it kind of flares out towards the end, okay? And intuitively, I think this makes sense because we have the least amount of uncertainty in our line in the center of all of our data. X bar and Y bar, that's the least amount of uncertainty. And as we go towards the edges with where we're far from x bar, we have more uncertainty, and so the confidence region flares out. And mathematically, this is seen, if I go back even further, if we look at the standard error term, we see that we have x star minus x bar, saying that the farther we are from x bar, this term is going to grow, and so the standard error of our estimate also grows. Okay. Is that okay? So this is a 95% confidence interval for the regression line, the true line that relates x and y. Okay. Of course, it doesn't count for the unknown error. Prediction intervals. Let's talk about prediction intervals. Oh, so this is me just repeating more of myself, I guess, but just kind of pounding this this idea home. Okay. The mean value, okay, expected value of y given x equal to x star. This is a parameter of the population, or you can think of it as a parameter of the population. It is a fixed but unknown quantity. Okay, so we're still using terms like 95% confidence and not 95% probability because it's a fixed thing. There's no uncertainty about it. It's just unknown to us. Okay. On the other hand, a prediction interval creates an interval for random realization of y when x equals to x star. Okay, so y star itself doesn't have to be on the regression line. We actually would not expect it to be on the regression line. Okay, and so because these are random realizations, it would actually be okay to talk about probability associated with these things because it's no longer a fixed thing. Okay? Oh, I was supposed to build this up. So just pretend like you only see the top part here. Okay? So the prediction interval, this is what it is, okay? You take your estimate with your beta hats, so this is the regression line, plus or minus, and you give yourself kind of the margin of error here, but it's for prediction interval, so the terminology changes a little bit. And this is what we have here, okay? And if we compare this, so now that I've shown you this, we compare this back to the equation that we used for confidence interval, we notice they're almost exactly the same. The only thing that is different is that this one has a 1 plus over here, and this one doesn't, okay? And so, yeah, this is the only difference, is that this thing now has an extra 1, okay? And how big of a difference does it make? It actually makes a significant difference here. And this is just a very, very brief kind of, this is about as much proofiness as I'm willing to type out on a slide here. Is that, you know, if we think about what the prediction interval is trying to do, we have to think about the variance between a random realization of y star and the difference between that and any given prediction y hat for x equal to x star. Okay, so this is this represents kind of the uncertainty in our prediction line, kind of the confidence interval, not really the confidence interval, but the uncertainty of our estimate of the prediction line, and this is the uncertainty in just any value drawn from y, okay? And so, you know, the rules of variance is the variance of this quantity is going to be the variance of y star plus the variance of this thing, okay? And so, you know, I skipped the math here, but the variance of this is sigma squared over this. So if I scroll back to these things, basically you just take this and we square this. So this is the standard error, but if I square it, I'm going to get this component over here, and then the variance of y star itself is sigma squared, right? So the variance of y star is the variance of the values around the line, and that's sigma squared that we're going for. Okay, and so so now we can factor this out, and we have sigma squared times 1 plus everything that's inside there. Okay, but of course we go about replacing sigma with s, and that means we use the t distribution rather than the normal distribution and all of that stuff. Yes?
Where's the covariance in the equation?
Covariance? I don't think, you don't need a covariance here because we're doing it for fixed values of x star.
Right.
So we're not worrying about how things, so we're saying for this given value of x star, how do the values of y vary?
Mm-hmm.
So the covariance would be 0, right? Because we're treating it as a fixed x. Yeah? Or no?
I don't understand, but maybe I can talk to you more after.
Okay, sure. Okay, so anyway, we have this, and R can calculate prediction intervals for us. Oh, I did this wrong. This should say predict, not confidence, did I? Okay, so instead of confidence, it should say prediction, and it would do it, okay? So I did this wrong, okay? But so replace this. I'll have to fix this in the. I'll be sure to fix it. So it doesn't say confidence. You just replace this with prediction, and it will do it. I have it right here. Okay. If we want to graph it, though, there's no nice native function. You can't just do like ggplot add the prediction interval. Okay. That doesn't exist for us. So what we have to do is we have to create the prediction intervals ourselves. Okay. And so this is kind of code to do that. And so essentially I'm creating a data frame, and I'm just taking and I'm defining new values of run size, and I'm just going sequencing from the smallest value in our run size to the largest value that we see in our data frame. Okay, because you know we'll talk about applications of regression. But you're not supposed to use your regression equation to make predictions outside of the range where you've collected data, right? Classic example is, you could take children's growth height over the years, and if you look at a child's growth from age 3 to age 10, you'll say, oh, this child grows every single year, therefore I'm going to predict by the time he's 100, he's going to be 30 feet tall or something like that. Okay, we know that's silly. You're only supposed to make predictions or use your regression line inside the zone where you've collected data. So I'm following that by going from the smallest value in our x's to our largest value of our x's. And I'm saying create a sequence where the output length is 100 values. Okay, and so it does that. And then so right now there's only just one column in predx as a data frame, okay? And then we're going to say make a prediction interval data frame where we're going to bind the columns of the x value, okay, that one column run size, and then we're binding it to the output of prediction where we're using the model and we're feeding it as x values what to use for our new data. And we're creating a prediction interval. Are these lines of code okay? It's a little too complicated? No, we're okay. When you replace your own data with it, it'll work. Okay. You just have to be careful with the variable names, right? So it's when you create the prediction interval, you use this function predict. You've got to supply. It's expecting in the data frame to have the name run size or whatever is being used as the x. If you just say x, it's going to say, I don't know what to do with x, okay? Because the way we've defined our model is runtime is as explained by run size, okay? So it tries to match these names, and if it can't match those names, it's going to get confused. So not about 99% of your problems, but a lot of your problems can be resolved by just being careful and just making sure your names match or spelled the way they're supposed to be spelled. Okay, and so we see this is what our data frame now looks like. Okay, and we've got fit with the lower and the upper. And then we can create this with ggplot2. This is now, the commands for creating this is now very different. We have to create our ggplot based on our prediction interval, okay, not production data. And then, and we say x is run size and y is our fit. And it's going to create kind of just our frame here. We add points, the black dots here, based on our production data, but then our smooth line and the region is added using this command, okay, where are the lower and upper bounds, ymin and ymax, we use the command identity saying I've actually calculated the values here. Okay, don't try to do any math here. So anyway, this code I'll put the R Markdown code up on online so you can edit this. I'm not expecting you to. Whoops. I don't want that. No, thank you, NVIDIA. Okay, so is that okay? Creating prediction intervals, and so we see this kind of makes sense in terms of a prediction interval that it looks like all of our data points. We're expecting about 95% of our data points to fall within our prediction interval. Whereas with the confidence interval, the data points don't necessarily fall inside the confidence interval because it's a confidence interval for the line and not for individual realizations. Okay, let's talk about ANOVA. Or do you have any questions before I get into the ANOVA? Yes?
So here you're predicting, or you're trying to find a confidence interval for the interval rather than the values?
No, this is a prediction interval for, so it's a kind of a, where we're 95%, we have a 95%, I guess, probability. Let me be careful about these words I'm using. We're about predictions of individual realizations of y. Okay, so it's not, so the confidence interval is for the population regression line, the mean regression line that exists in the population that's unknown to us, but is fixed at something. That's the confidence interval. This is a prediction interval, which is used for individual data point predictions at certain values here. So that's why it's like much wider. Okay. All right, so let's talk about ANOVA. ANOVA stands for Analysis of Variance. And the big picture of ANOVA is that we're taking the total variance in our response variable. So whatever our y variable, we're looking at the total variance there, and we're trying to split it up into different components or different pieces. Okay? And so, for example, let's say we wanted to explain the variance in used car prices. Okay? So you go to a lot and you look at used cars, you see, oh, this used car I can get for $5,000. This used car still costs $20,000. You know, how do we explain all of these different prices I see, right? So we've got a total variation in our response variable, and we say, oh, well, if we think about it, there's a whole bunch of different things that go into determining the price of a used vehicle. We've got the make, we've got the age, the mileage, the condition of the car. All of these things go into determining the price of a used vehicle, right? And so what ANOVA does is says, okay, the total variance is this amount, and we're going to say like 20% of the variation in price can be attributed to the make. 35% of the variation in price can be attributed to the age. 10% of the variation can be attributed to this thing, and this amount of variation can be attributed over here, okay? And that's what ANOVA is doing. There's always going to be a leftover part that is not explained by the model, right? Because you could have two cars that are the same make, same age, same mileage, and same condition, but one might be worth $500 more than another car. Okay, how do you explain that leftover 500 part? Okay, well, if your model only has these 4 things going into it, it's just stuff that's left out of the model, right? Maybe there's finer, little things. Did you have leather seats or fabric seats or whatever? Okay, these little things might play a difference. And so because your model doesn't account for everything, there's always going to be something left over, and that's called the residual in our variance. Okay, so whatever your model doesn't capture, there's going to be some variation left over. That's called the residual. So there's always going to be something left over, unless you've perfectly fit your model, which generally is a bad sign that you have done overfitting. Okay. So when we're doing ANOVA for simple linear regression, we only have one source, one variable to explain the variation in y, and that's our x. So when we do our ANOVA, it's only going to split it into 2 parts. The variation the variation in y that can be explained by x, and then the residual, everything left over. So there's only going to be 2 parts when we do ANOVA for simple linear regression. Okay. And so, and when we're working with ANOVA, we work in sum of squares. Okay, so if you just think of the variance, the sum of squares is just the numerator in the variance. Okay, so this total sum of squares total is sum of y. This is just going to be the difference between each value of y and the mean of y squared. And we do this for all of our data points, and this gives us our total sum of squares. So that total sum of squares is going to be split up into 2 parts. The sum of squares accounted for by our regression model, and then the sum of squares that's not accounted for by the model, which is called the residual sum of squares. Okay, so we split this quantity, whatever this is, into sum of squares from the regression model plus residual sum of squares. Okay, and so this is at least for ANOVA for simple linear regression. We're trying to take the total variance, and we're trying to say this much of the variance is because of this part, this much of the variance is left over. Okay, so we have total sum of squares is that. The residual sum of squares. Okay, this is the sum of squares that's not accounted for by our model. Okay, so this would be the difference between each value and our predictions for that value, right? Because our model says things should follow this line here, okay, or whatever, this line. And of course, each individual data point doesn't follow that line exactly. So whatever the difference is between our line and the actual data point, that is our residual, and we square those and we take those. So residual sum of squares, this is pretty much the definition of a residual, and we're squaring it, and we add those up, so that's residual sum of squares. All right, y minus y hat. And then the sum of squares regression, this is the difference between what our prediction is according to the model, which is our y hat value, and then what our prediction would be if there were no predictor. Okay, so I think at the very beginning of the course we said if you weren't given an x value, or if you weren't given any information, what's the best guess that you should make? And we said the mean, right? If you didn't know anything, the best guess you should make is the mean if you're using the squared loss function or penalty function. And so the difference between the prediction that we make, y hat, and y bar, this is our sum of squares regression. Okay? And we take these differences, we square them, and we add them up. Does that make sense? The sum of squares regression, why it's this quantity? It's because if we had no information from x, our best guess would just be y bar. But we're adjusting that based on the information we have on x, and so that goes into our sum of squares according to the regression. Okay, and you can show that this quantity plus this quantity will equal this quantity. Okay, and we put this all together in the ANOVA table. Okay, and so the ANOVA table, we say, what are your sources of variation? And for simple linear regression, we have two sources. This variation accounted for by the regression, the residual variation. We have degrees of freedom associated with each of these things. We got 1 degree of freedom with associated with the regression, and then n-2 associated with the residuals for a total of n-1 degrees of freedom. The sum of squares comes from the previous page, which shows up here. Okay, and then this ms is known as mean squares, and that's just basically sum of squares divided by degrees of freedom. So in this case, mean squares is equal to this because dividing by the degrees of freedom is dividing by 1. And then the mean squares over here is you take this and you divide by n-2. Okay, but the mean squares, whatever it is always sum of squares over degrees of freedom. And then you take the ratio between this quantity and this quantity. And this gives you the F statistic. All right, now, I don't know if I want to explain the F distribution, but the F distribution is the ratio between two T distributions. And, well, anyway, this is how we decide if something is significant or not. But this is the F statistic. But anyway, if you look at an ANOVA table, this is generally what it looks like. Okay, so I'm just kind of showing that. And so when we go to R and we say, hey, give me an ANOVA table, we have, it says run size, so because our current model just says we're predicting run time based on run size. So our entire model, the regression model, is just based on this one thing. So that is our source of variation, run size. And we see degrees of freedom, the sum of squares, the mean squares, and the F. Okay, and then we also have the residuals, mean squares, sum of squares, some degrees of freedom, sum of squares, and mean squares. Okay, and so, you know, you could do this manually, and you could see that this divided by 1 is this. This number divided by 18 gives me this number. And this number divided by this number gives me 48.717. So if you wanted to, you can verify that all of these numbers are indeed coming from what we said here. Okay, and a classic, you know, if we had a pen and paper test, a classic pen and paper problem is, you know, they print out something like this, and then they white out certain numbers, and they say, well, because you have these numbers, figure out the missing numbers and things like that. It's like a classic stats problem, but we won't do that here, okay? What was I saying here? I forget why I put this in here. That's okay. Okay, so I wanted to do, I think, yeah, we got some time. I was going to create a manual regression table, or a ANOVA table ourselves. And so I'm going to go back to our silly toy data set with the bedrooms and closets, right? I like it just because there's 4 data points, but it captures what I want to try to do here, okay? And then I get to play with my tablet. No, not really, but okay, so anyway, we're gonna fit this, and so what was that last Friday? Did we show how we got the correlation R squared for, not R squared, but just R for this? Okay, and so if we so we're gonna take our data here, and let me, so this is our data. Oops. Okay, so I've got my x. This is bedrooms, and then y is the closet, right? And then we fit our regression model. Y hat is equal to 1 plus 1.6x. Okay, and so we could plug in each value of x. So if I plugged in 1 for x, my y hat, this is what fit is, we can see that this is indeed what we would get. So if I plugged in 1, I would get 2.6. If I plug in 2 for x, I would get 4.2, et cetera, et cetera, et cetera. Okay? All right, so what we're going to do is we're going to find the sum of squares according to the regression, and then we'll also find the sum of squares residuals, and then I'll also show that it equals sum of squares total. Okay? Or not, sum of squares, this is actually RSS, sorry. Okay, so sum of squares regression. So if we let me also just graphically illustrate this. So I want this, and then I want this, and then I gotta do library ggplot2, and then we want ggplot dwell asx equal to x equal to x, y equal to y, plus geom. Oh, I hope everything's okay. Plus stat smooth. Oh, I forget. I think method equal to lm and se equals false. There we go. All right. All of this work just to get this picture. All right, and let's put this into our little diagram as well. Okay, so we have this thing, and stop. I need a. Okay, so what we're doing is we're saying if we look at the total sum of squares, let's do this first. Okay, we just want to look at each data point y minus y bar, and we're gonna square this. So we're kind of getting at the idea of the variance, but we're not dividing by n minus 1. So we say, okay, y was 2, and we're going to do 2 minus the y bar is 5. So we do 2 minus 5 plus 6 minus 5 plus 4 minus 5 squared plus 8 minus 5 squared. Okay, so I have 3 squared plus 1 squared plus 1 squared plus 3 squared. I have a total of 20, right? 9 plus 1 plus 1 plus 9, yes, 20. Okay, so my sum of squares total is 20. And the idea there is I'm going to draw kind of a red line at y equal to 5. Okay, so this here represents y bar. And so the total sum of squares for this, I'm going to just draw a green line. So this is kind of, we're getting at the difference between each dot and the bar. Okay, and so if we square each of these green distances, this would be sum of squares total. Okay, so green line squared. sum of the green line squared. Okay, and we get 20 there. So the sum of squares regression, though, is, let me see if I can find another color to use. So I'm going to use this purple or magenta or whatever. And we're going to say, okay, well, now that I know what x is, instead of predicting 5, I'm going to predict, that color looks exactly the same as red, huh? Maybe we'll use this cyan, okay? So instead of predicting, that looks the same as green. Well, my life is hard. Okay, we'll use this blue. Okay. So instead of predicting 5, I'm predicting 2.6. So this difference is going to be 2.6 minus 5, and I'm going to square it. And then instead of predicting 5, I'm predicting only 4.2. Okay, so I'm going to have 4.2 minus 5 squared, and instead of predicting 5, I'm predicting 5.8 right here. 5.8 minus 5 squared plus, and then lastly I'm predicting what I'm predicting 7.4 minus 5 quantity squared. Okay, and so I get no, what is this? 2.6 minus 5 is 2.4 squared plus 0.8 squared plus 0.8 squared plus, oh, this is 7.4, 2.4 squared. Okay, can someone do this math for me? I'll do it. 2.4 times 2.4, 5.76 plus 0.8 squared is 0.64, and then I can multiply that by 2. So I get a total sum of squares regression equal to 12.8. Okay, is that good with everybody? Okay, and then lastly is, okay, well, here's my prediction line. The actual dot is not on the prediction line. The difference between the prediction line, can you guys even see that yellow? I can't see it on my screen, but it shows up on the screen over here. So the difference here is the yellow. So this one is the blue line squared, and then over here will be yellow square. Okay, and so over here our regression line is actually taking us further away from the estimate than y bar, but that's okay. We're gonna add all of these up together and see what we get. Okay, so let's I'm just gonna use black over here. Okay, so the actual value of y down here was 2, but we predicted 2.6. And over here the actual value of y is 6, and we predicted 4.2. And over here the actual value is 4, and we predicted 5.8. And lastly, the actual value is 8, and we predicted 7.4. Okay, and so if we do this, we get 0.6 squared plus 1.8 squared plus 1.8 squared plus 0.6 squared. Okay, and then so punching these out, 1.8 times 1.8 is 3.24 plus 0.6 squared, which is 0.36. And so a total sum of squares according to the residual of 7.2. Okay, so we see that sum of squares total, which is 20, is indeed equal to sum of squares regression plus residual sum of squares. This is equal to 12.8 plus 7.2. Okay, so that's nice, right? And I'll save this and post this online as well in case you want. what are we? 101A, and it's October 7th. Oh, and then we're going to run out of time. Okay. All right, so anyway, let's create our table. All right, so we have sum of squares regression, residual sum of squares total as our source. Then we have columns degrees of freedom, column sum of squares, column mean squares, and our f. Okay, so the sum of squares total is n minus 1, so we have 4 data points. 4 minus 1 gives me 3. We're always going to have 1 for the sum of squares regression because we only have one thing predicting it, and then so these have to add together and we get 1 and 2. Sum of squares regression we found to be 12.8. Residual sum of squares we found to be 7.2. These were the numbers that we got on the previous page. So far so good? Okay, and so our mean squares is going to be 12.8. We do 12.8 divided by 1. And our mean squares over here is going to be 7.2 divided by 2. So this gives me 7.2 divided by 2, which is 3.6. And our f is going to be 12.8 divided by 3.6, which is something. 12.8 divided by 3.6, and we get 3.555. 555, so I'll just round off to 6. There. Okay, so this is our ANOVA table, and we see we see how what it tries to do is it splits our total sum of squares, which is the difference between each value and the y bar, and it tries to split that into 2 parts, a blue part and a yellow part. The part according to the regression and the part that's still left over. And sometimes it's okay, our regression takes us in the opposite direction, but that's okay, and we get that. So, and if we go back to R, and I say, okay, create an ANOVA, what we see is that this ANOVA matches matches what we have found manually in our thing, right? So this is okay, so that's nice. Okay, so the our ANOVA table matches the R's ANOVA table, okay, the one from R, 12.8 and 7.2 with the mean squares and the F, okay? And so, so I hope this at least sheds some light into what ANOVA is doing. It's taking, and I hope, oops, I'm hoping this kind of shows you that we're instead of the total sum of squares is the difference between each data point and the mean line of y bar, and we're parsing it into 2 parts, the part that can be accounted for by our regression and the part that is left over, okay? And so the we get this r squared value, okay? Okay, so if you remember, r squared for linear regression is going to be little r squared. So we have 0.8, our correlation was 0.8, and we have 0.64. Over here, we can also think of this as how much of the total variation or total sum of squares is not accounted for, or is accounted for by the model, okay? So we can think of this as 1 minus, and we're going to do 7.2 over 20. This is the kind of proportion of variation unaccounted for, right? Proportion of variation that's in the RSS. I guess, you know, in this case, when we only have 2 sources, you can just do 12.8 divided by 20, but this is the proportion of variation not accounted for by the model. Okay, so if I do 1 minus 7.2 over 20, I get 1 minus 0.36, and that is also 6.4. So we see that the quantity r squared, which we get by squaring the correlation, is also tells us the amount of variation that is explained for by the model. 12.8 of our total sum of squares out of 20 is explained for by the regression. So 64%. Okay, so I hope that's good, and I hope between the commands that I have in these lecture slides, you can get at the homework. And I will have office hours tomorrow, and we'll spend some time on Friday just going a little bit more over our stuff as well.